So, the previous lecture we have seen examples of groups, we have seen lots of situations where groups arise naturally, and we also synthesized the definition of groups after all the discussion. And I said last time that groups are born to act. So, group action is something which is very important concept all throughout the cases which are there in this course. I said symmetry, puzzles and motions. All these three things, actions are something which are at the center. They are the most important, that's the most important concept. So, I am going to discuss what group action is and related concepts, Orbit-Stabiliser lemma, orbits and stabilizers. And you remember the example that I had last time, that is something that we are going to have the back of our mind. That was a rectangle, and we could perform certain symmetry operations on it, doing nothing, flipping about x-axis, flipping about y-axis and rotating it by angle of pi, right? And this we said forms a group. So, that is an example that we are going to keep in the back of our mind. Okay. So, let me take certain point here. Let me call this point say P. So, group, we understand it is a collection of symmetries of this rectangle, and I consider a set. What is this set? This set consists of all the shaded region along with the boundary. So, suppose this is 2, 0 and this is 0, 1, suppose that is a rectangle. Then I consider all those points A, B for which mod of A is less than or equal to 2 and mod of B is less than or equal to 1. That is this rectangle, right? The shaded region along with the boundary, that is X. Now, let me take say Fx. What happens to P when I apply Fx? That is, when I flip about x-axis, what happens to P? P goes here. Okay. So, this is what P after the action of Fx. So, through this example only I am going to define action, and if I apply effect the other action, the action of Fy, then it will be somewhere here, and that is what I call Fy dot P. Okay. And this point will be here somewhere, R pi dot P. So, under the influence of this group, that is through the group action, P moves from this position to this position, this position and this position, these 4 positions it can move to. Okay. So, that is the basic thing. So, formally I am going to define the action now. In the action there is a group and then there is a set. I have already given you a concrete example of action through the rectangle and this group case. Okay, so what is a group action? I have a group. Recall that group was collection of objects along with certain operation which followed certain axioms that I discussed in the last class. So, here is a group and here is a set. So, I have group, I have a set, and I say that G acts on X. When do I say this? When there is an action. And what's an action? So, as was happening earlier, I pick a point in the set and I pick an element in the group, and under the influence of this element of the group, the point P moves somewhere within X, and this is what I call G dot P. That's just a notation. I call G dot P. So, I pick some element from the group, pick an element from set, and it goes to some other element of the set. There should be certain axioms which have to be satisfied before we call it an action. Identity element of the group is not allowed to move any point. That is first axiom. Action of identity on P is just P. It's the first axiom. So, these are axioms for the action. 1 dot P is P. Second is interesting one. I take the point P and I take two elements, G comma H, G and H in the group. So, first with the help of H, I try to move P, that is I am considering the image of H comma P under this map, so H dot P, and then I am trying to move whatever is the resultant, I am trying to move it by action of G. What I could have done is that I could have tried to move P by the action of GH. When I write GH, GH is an element of G. It is a group law. It is a group law, right? So, for this map G cross X to X to be called an action, I want this to be equal. I want that action of H on G followed by action of G on HP. So, that action is just same as the action of GH on P. So, that is action, and as you can see, this is precisely what happens in the example of rectangle that I had, when on the rectangle the group of 4 element acts. I am back here. Now, there are other concepts, orbits and stabilizers. So, let us pick this particular point. Orbit meaning under the influence of the group, where all can this point P go? As we can see here, if point is somewhere like this, it can go here, it can go here, it can go here. After the action of, this is Fx after the action of Fy, and this is after the action of R pi. So, it can move across these 4 points. What if the point P were here on the x axis itself? If that were the case, then under the action of Fy, it would go to this point, but under the action of Fx, it will remain here, and under the action of R pi, it will again go here. So, point here is going to have 2 elements in its orbit. Okay. So, what is orbit? I will just write here. Orbit of a point P. P is in X. What is orbit? Orbit is start with P, and where all can P go under the influence of the group G dot P such that G is in G, that is orbit. So, as you have seen, this point has 4 elements in the orbit, while this point has only 2 elements in the orbit. And if I take this origin, then orbit is just the origin, because whatever thing I do 1 fx, fy or r pi, this point is not going to move. There is only one element in the orbit. So, that is orbit. There is another concept which is that of stabilizer. So, stabilizer for a point P is the collection of all those points of the group, that is all those points of the group G in G, such that G does not move. G does not move P, that is G dot P is simply P. All those points of the group, all those elements of the group which fail to act on P in a non-trivial fashion, that is called stabilizer. So, what is orbit? Larger the orbit, meaning the point is moving the point is having much more space in the set X, but if orbit is small, then point is moving slowly, right? You see this point, this is having smaller orbit, it is moving only here and here, but if point is this, then it is having 4 elements in the orbit. And so if orbit is small, as the intuition says, stabilizer will be bigger. So, smaller the orbit, bigger the stabilizer. For example, you consider points which have singleton orbit, that is orbit is just one. No point in group is moving that point. So, no point of the group is moving a given point of the set. That means stabilizer is everything, right? So, if orbit of P is singleton, then stabilizer of P, so I will also call it just stabilizer of P is everything, right? And such points are called fixed points. They are just fixed throughout the action. No element of group is able to move those points. Okay, as you can see in this example, this is the fixed point. This is a fixed point in the action. Okay, so here in this example, there is only one fixed point, and for this fixed point, all 4 elements constitute stabilizer. So, this is some kind of conservation law, right? Orbit and stabilizer. Orbit is bigger, stabilizer is smaller, orbit is smaller, stabilizer is bigger. So, what we have therefore is orbit stabilizer lemma. So, it is true for finite groups. So, I will explain what it is. So, I will just mention it here. Orbit stabilizer lemma. What does it say? It says that you take a group which is finite and you take a set X such that G X on that set and say X is also a finite set, and then you pick any element in X. You can consider the stabilizer of this point. This is set. You can consider the size of this. This mod is size of the stabilizer. How many points are there in the stabilizer? And then you consider orbit of P, and then you consider size of the orbit of P. These are two numbers. Multiply these two numbers. Multiply the size of the stabilizer with the size of the orbit, and what you have is actually size of the group. So that is called Orbit-Stabiliser lemma. This is some kind of conservation law. Larger the orbit, smaller the stabilizer. And why should it be true? That involves some quotient groups, or rather taking cosets, and I am not going to say much in detail about it. So this has something to do with cosets. For example, in this case, if your point is this, then the orbit size is 2. So let me call this point Q. For this point, you take stabilizer of Q. What is it? Stabilizer of Q is of course identity. Identity is always stabilizer. And apart from that, if you take flipping about x-axis, that is also stabilizer for this point. So stabilizer is size 2. And what is orbit size? Orbit of Q is, again, there are 2 points in the orbit, this point and this point. So the product, so stabilizer of Q times orbit of Q is 2 into 2, 4, which is precisely the size of the group. Just through the example, we have tried to understand this thing. So I hope now it's clear to you what an action is, what orbit is, what stabilizers are, and what is Orbit-Stabiliser lemma. Okay, so let me just try to give you a picture. Just imagine, imagine this is some set X on which a group G is acting. Now I take a point P and I can consider all those points where P can go under the influence of G. So P can go to various points. So I consider all those points which are there in the orbit of P. So whatever is outside it, some other point, say Q, I consider orbit of that. Some other point R, I consider orbit of it. The question is how to count how many orbits are there, and that's quite interesting question, has very interesting answer and has very interesting applications. So question is, how many orbits are there for a group action, for a given group action? G is a group, axis is a group action which is happening as a finite group, how many orbits are there? And it's quite interesting answer. And before I could give that answer to you, I would define one more concept, which is that of fixed points. So here I pick an element in the group and I find out all those elements in the set which are fixed by G. That means those points are not moved by this particular G. So I consider all those points P in X such that G fails to move those points. For example, if G is identity, then by definition of action itself, everything is fixed. 1 dot P is equal to P. That's the first axiom in the definition of group, right? So when G is identity, everything is fixed. So fixed points are quite interesting. Those points which are not moved by a given element in a group. And what I am going to say is that the question that how many orbits are there for a group action, that question has connection with number of fixed points. Now what's the connection? And that is Burnside's lemma. What does it say? It says that for each G, you consider how many fixed points are there. Take the summation and divide it by the size of the group, and that is actually number of fixed points in an orbit. It's popularly called Burnside's lemma. So what it is? This is average number of fixed points. So average number of fixed points equals number of orbits is what Burnside's lemma says. Now how to prove such a statement? It's not very difficult and it's quite useful, and I am going to tell you two interesting applications of Burnside's lemma. Okay, so I am going to prove Burnside's lemma. So we have to have some imagination. Let's do this. I am asking all the elements of the group and all the elements of the set to be expressed here in a Cartesian format. So let me take this as G axis, this as X axis. I have action of group on a set X. G is acting on X. So here I am marking elements of G, just a pictorial representation, and here I am marking, say, elements of X. Okay. So here just take some point here. Suppose this element is G, this is X, then this is say g comma x. Okay. So all these things are presented in the Cartesian format. And now I consider a subset of this. So you can think of it as lattice. It's a lattice which is there. So many points are there on this lattice, right? It's like lattice. It is g cross x. As a set, it's just g cross x. That's some lattice. So inside this lattice, I define a set S. What is the set? That set is g comma x. So this is a subset of g cross x. So all those elements g comma x for which g dot x is x. That is, x refuses to be moved by g, or g is not able to move x, the same thing. So g dot x is x. And the proof is just about size of S. How many such ordered pairs g comma x are there on this lattice for which g dot x is x. Now there are two ways to count it, and that is precisely what gives proof of Burnside's lemma. So what are the two ways? One way is I fix a g and then look for all the elements in this column for which g dot x is x, and then add it with the similar number for another g, another g, another g, like this. Or I fix one x, and then in the same row I look for all those g's which are not able to move this x. Okay. So I can do this calculation on size of S in two ways, column wise and row wise. There are two ways, and that is what is going to give me the proof of Burnside's lemma. So let's do that. So let me first fix g. I am fixing g. So I fix g, and then I ask for how many x are there which are not moved by this g. Okay. That is fixed g, right? Size of the fixed g. And then simply I am summing it over the whole group, right? And this is what is size of S. So here is another way of estimating size of S, which is you fix x, you fix an element x in the set, and then ask that how many elements of the group are fixing that x. That is the size of the stabilizer of x, and then you just take summation, and the two numbers are equal. This summation of fixed points when g is moving all across the group is same as summation of all the stabilizer where x is moving all across set x, and I just equate these two numbers. So before I do that, let me just make an estimate for the summation of sizes of stabilizers. So summation of size of stabilizers is actually equal to, we have seen Orbit-Stabiliser lemma is same as mod of size of g divided by size of orbit of x. orbit into stabilizer, size of order, size of orbit and size of stabilizer is equal to size of G. So here it is x in x. So when I equate these two, what do I get? I just take G on the other side and divide. I get that 1 divided by size of G summation G in G and then size of fixed points is equal to summation x in x 1 divided by size of orbit of x. Now let us pick one element here. Now our job is to estimate this. In fact, we are supposed to say that this is precisely the number of orbits in an action, and G x on x, this is the number of orbits. So let us see how much is the contribution from one element. Contribution from the one element x in x is 1 divided by size of the orbit of x, and therefore how much is the contribution in this summation from one orbit? It is 1 divided by size of orbit of x times size of orbit of x, which is 1. So one orbit is contributing exactly once in this summation, and therefore this is precisely number of orbits. This is precisely number of orbits in an action. So we arrive at Burnside lemma, which says that number of orbits is precisely the average number of fixed points in an action. What is the application of this? So I'll present two applications of Burnside's lemma. So here is quite interesting example, coloring a shape. So let me put a shape, very simple one. I'll take a square, and suppose there are two choices of colors available to me, say red and blue. I have two options. So each edge, each side of this can be colored either red or blue. Okay. There is a possibility where all four are red, there is a possibility where all four are blue. Okay. So question is, how many different shapes like this, how many different squares like this can you make? Well, there is a possibility where I have this red, this blue, this blue. There is a possibility where I have this blue, this red and this red, right? A priori these two things look at these two things look like two different possibilities, but not quite. If you treat these colored things as toys, one can actually rotate this. One can rotate it by 90 degree to obtain from this shape the other one, right? So as toys they are same actually, right? So if you are supposed to count number of different toys that you can create by this kind of coloring scheme, it's not correct to say that this is 2 to the power 4 choices. That for each edge I have 2 choices, there are 4 edges, the 2 to the power 4 toys are possible. That's not quite right to say, because you see there are certain situations where although in this count there are two distinct possibilities, but as toys they are same, because you can obtain this from this just by rotation. So, as toys they are same. So, what exactly should we do in order to count right number of toys? And idea is simple. Count number of orbits. And then you should ask, where is the action? Because you count orbits only when there is an action. So, then we have to see what is happening, what is x, what is g. Okay. So, here I can take x to be all 2 to the power 4 possibilities, the set of all 2 to the power 4 possibilities. And where is the action? Action is this. These are the things which keep the toy look same in the shape, but probably different in the color configuration. So, what is G? G is the set of symmetries of this object. In this case, this object is square. So, G is a set of symmetries of square. And what is the action? Action is quite natural one. Action is you take a particular configuration, take a possibility, it could be say RB or something, and take symmetries of rectangle, in this case it is square, take symmetries of square. There are 8 symmetries of square, and that could be an exercise for you. The way we proved, the way we got convinced that there are 4 symmetries of a rectangle, the same way we can also estimate that for a square there are 8 symmetries. Okay. So, suppose this symmetry is something like diagonal, flipping across one of the diagonals, say this diagonal, then this possibility goes to what? So, when you flip about this diagonal, B goes here, R comes here, R comes here, and R comes here. Okay. So, when under this action you count number of orbits, and that is when you actually get the right number of different toys that you can create. And in the exercise set, we are going to have some interesting problems and some problems which involve cube and tetrahedron. So, in the exercise set, we are going to have that. Okay, that is one thing why we should count orbits. Here is another interesting problem. So, maybe during the exercise part, the assignment part, I will give you this problem, but let me explain you what the problem is. Here is the class. Suppose there are n students, S1, S2, S3, Sn. There are n students, and each of them is having a pen, P1, P2, P3, Pn. So, as students, as n students are there and n pens, each of them is having their own pen. Teacher comes and randomly distributes these pens to these students. So, teacher comes, collects all these pens and distributes it to students randomly. So, possibly S1 gets the pen of P3, maybe S3 gets the pen of Pn, maybe Sn gets the pen of P2, or all this chaos happens. Now, question is, on average, and one has to devise the right meaning of on average. So, on average, how many students will get back their own pen? And for this, one has to understand what is the action which is going on. One has to understand what is the group involved and what is the set which is there. So, I'll just give you some hint. So, what is the group? What is the action? So, group is actually permutation group. The permutation is happening here, right? So, permutation group, which is the group. So, and action is what? So, this G is Sn. Which is permutation group. What is permutation group? I have said the last lecture that you have n distinct points, you permute them, and once again you permute them. What you get is again permutation of the original configuration, permutation of the original objects. So, if you collect all possibilities, all n factorial possibilities of all possible permutations, it forms a group. You can compose two permutations and it is again a permutation, and the original configuration itself is one of the permutations, identity permutation, and for each permutation there is a reverse permutation which brings it back to the original configuration. So, set of permutations is a group, and this is a group of size n factorial, right? There are n factorial possibilities of permuting n objects. Of course, we are assuming that those objects are not tied to each other, they are not bound to each other, okay. So, there is no restriction in the permutation, we are permuting them as discrete objects, as independent objects, okay. So, that is permutation group, and the notation for the permutation group is Sn, and the action which is happening in this problem is this. So, what is happening? I take an action, I take a permutation, let me call sigma, and then you pick one of the pens, suppose pen of the ith student, and then you take it to j, where Sj gets pen of the ith student. That's the action. So, hint is that of course the action is this. Action is Sn, the permutation group acting on the set of n elements, natural action, and what we are supposed to count is average number of students who get back their own pen. So, maybe we are talking about average number of fixed points, and that is a hint. So, probably it has something to do with average number of fixed points. I won't give you a hint beyond this because this is going to be one of the exercise in the assignment. So, next time we are going to learn about applications of group actions in understanding some puzzles, applications of group law in understanding some puzzles, and the keyword is going to be parity. Groups can be used for parity checking. So, I will see you again in the next lecture. Thank you.